In the last section of the book, we concentrated on average rates of change. In this section, we want to start our discussion of instantaneous rates of change, but there'll be a very serious technical difficulty that we'll have to fix in the next section, which will be very technical. But in this section, we can do intuitively what an instantaneous rate of change is. So let's return to the problem that we started with in the last section of a car traveling down a straight road at at noon. The car is at mile marker 37. Two minutes later, the car is at mile marker 38. And now, my question is, what was the velocity of the car at noon? And for convenience, why don't we just say that we're going to call noon our time 0. So our time is measured in hours from noon. So that t equals 0 means 0 hours past noon, so at noon. So what was the velocity of the car at noon? Well, who knows? At least this data doesn't tell you what the velocity of the car is at noon. This data, as we saw last time, tells you the average velocity of the car over those 2 minutes. What we calculated last time was that, the average velocity of the car was the change in position, so delta position over delta t, the change in time. And this was 1 mile in 1/30th of an hour. So the average velocity was 30 miles per hour. Great, great. So what? We want the velocity at noon. Do I mean the average velocity at noon? No, that has no meaning. We talk about the average velocity between two times. So we could say between noon and 12:02. But the velocity at a time, there's no choice. That can't mean an average velocity because only one time's been specified. This velocity has to mean the instantaneous velocity. There's no choice. Now, frequently I will emphasize that it's the instantaneous velocity by saying instantaneous. But if we talk about the velocity at a time, that's what it has to mean. So the velocity at noon, so let me make this clear, the instantaneous velocity. Okay. Can we tell from this data what the instantaneous velocity of the car at noon is? No. Can we approximate it well? Probably not. I mean, the car averaged 30 miles an hour. The car averaged 30 miles an hour over those 2 minutes. Does that tell you in any way, shape, or form what the velocity was at noon? No. The car could have been going very slowly at noon and sped up to average this. So the car could have been going 10 miles an hour at noon and then sped up to average 30 miles per hour. The car could have been going much faster and braked hard to average 30 miles per hour. How do we know what the velocity of the car was at noon? Well, it's easy for the driver of the car. The driver of the car looks at the speedometer and sees her speed. As I mentioned last time, there's a difference between speed and velocity. Velocity includes a direction. So, okay, she not only looks at the speedometer, she also notices which way she's going on the road. In any case, the driver of the car can look at the speedometer and notice which way she's driving on the road and know her instantaneous velocity, if you believe the speedometer is accurate. But how does someone outside the car know the velocity or approximate the velocity? It's clearly this calculation that the average velocity is 30 miles an hour is almost useless. How would you get a better approximation to the actual velocity of the car at time 0, so at noon? Well, you take, the velocity of the car could have changed too much in 2 minutes. So you take a smaller time interval over which you don't believe the driver could have, or anything else, could have affected the velocity of the car very much. So how about instead of t equals 0 and t equals 0 plus 2 minutes, we take a look at, what if we look at the average velocity between noon and 10 seconds later. Maybe this would be good. So I'm just assuming that we know the position of the car 10 seconds later. There aren't mile markers. There aren't fractional mile markers, or there aren't many of them anyway. So yeah, we would have to have positions marked out along the road or somehow measure the position of the car at smaller time intervals. But assuming that we can do that, what if we look at the average velocity of the car between noon and 10 seconds later? So we take the position of the car at noon plus 10 seconds, and we subtract the position of the car at noon, and we divide by the 10 seconds, converting it to hours if we want miles per hour. Maybe that would give us a good approximation to what the driver of the car sees on her speedometer. Well, yeah, maybe, but maybe not. 10 seconds is a long time. And again, she could have stomped on the accelerator or stomped on the brake and radically changed her velocity in 10 seconds, so that knowing even the average velocity between noon and noon plus 10 seconds might not be a good approximation. Even if you know that, you might not have a good idea of what her actual velocity was at noon. So, well, how do you do that? Well, don't take 10 seconds. How about 1 second later? All right. If we take the average velocity of the car between noon and noon plus 1 second, do we believe that that would be a good approximation to the actual velocity of the car at noon? Pretending for the moment that we can actually measure the change in position in 1 second accurately. That might be a good approximation to the velocity at noon. It could be. In 1 second, some cars are really responsive. You see these acceleration times and braking times. Maybe 1 second is still too big a time interval. Maybe the velocity could change pretty radically still by stomping on the accelerator or the brake. All right, let's try 1/10 of a second. Surely that's enough to get what most anyone would call a reasonable approximation to the velocity of the car at noon. You take the position of the car at noon plus 1/10 of a second, subtract the position of the car at noon, and divide by 1/10 of a second, or the appropriate fraction of an hour if you want things in miles per hour. Okay, 1/10 of a second. Yeah, that sounds good. So why don't we stop there? Why don't we say, okay, her instantaneous velocity, the instantaneous velocity of the car is what you get if you do this calculation. What's wrong with that? What's wrong with that? There are at least two things. There are at least two things wrong with that. One is that why stop at 1/10 of a second? I mean, if we're assuming we can measure the position a tenth of a second later, why not assume we can measure it a hundredth of a second later or a thousandth of a second later? Why not take as small a time interval as possible? And secondly, physically, we don't want to describe instantaneous velocities this way because it requires us to know something about the physical properties of what we're talking about. We have to know that the velocity of a car really can't change much in a tenth of a second. But what if we want to talk about the velocity of particles or photons or I don't know what, comets or other things that move very fast? Maybe a tenth of a second isn't good in other physical situations. Maybe that's too big a time interval and the velocity could change too radically in that amount of time. So we don't like calculating, we don't want to use the average velocity over a 1/10 of a second interval. We'd like to take kind of no time interval or kind of the smallest possible time interval. So it will help if I write some more things at this point, but let me try to make this more clear by writing more math. Suppose, let's pick on the metric system. Suppose P of t is the position of anything on a straight line where we've laid out a coordinate axis. The position of a car, a particle, I don't care what it is. Suppose P of t is, I'll say a particle, is the position of a particle moving in a straight line, but that's all we're going to talk about in this course, so I won't say that every time. Suppose P of t is the position of a particle in meters at time t seconds. Then what I've said is that we would like to look at what should instantaneous velocity be? What is the instantaneous velocity of the particle at t equals 5 seconds. You should, of course, complain, I haven't given you what P of t is. Right, even without giving you a formula for P of t, we would like to answer this no matter what P of t is, but assuming that we know it. The question is, what should it even mean? And what our discussion over there should tell you is we want to look at the average velocity delta p over delta t for very small changes in t. So for very small delta t. How small is very small? Really, really, really small. We want it to be, we can't let it be 0, but we'd like to let it be 0, but we can't. So what is the average velocity between times t equals 5 seconds. I'm going to drop the units. We know their time is measured in seconds in this problem. Between times t equals 5 and here's what we do. We just say between times 5 and 5 plus a little bit, and then we see and t equals 5 plus h, where h could be negative, so that this is actually a smaller time. What is the average velocity between times 5 and 5 plus h for very small h? Small does not mean really negative, like negative 5 million. We don't mean small in that sense. We mean close to 0. So for h, very close to 0. So what is this? By definition, it is you take the position at time 5 plus h, you subtract the position at time 5, and you divide by the change in the positions, the changes in time. So 5 plus h minus 5. And so you get p of 5 plus h minus p of 5, so the change in position over just h, which is the change in time here. So you get this, and what we'd like to know is, what does this do? What is this as h gets very small? How small? Really small. We'd like to let h be 0, but we can't do that, because if you let h be 0 in the numerator, you get 0, in the denominator you get 0, and 0 divided by 0 is not defined. So we can't let h be 0. You might say, well, let it be the first positive real number. There is no first positive real number. Between any two different real numbers, there's always another real number. So if you think, oh, there's some first positive real number, we'll take half of that. It'll be smaller. So we can't let it be the smallest positive real number or smallest negative real number. We can't let it be 0. Then how do we solve our problem? We let it get as close to 0 as we want. And we see what happens as that happens. So, yeah, what we would like to do is see if this gets closer and closer to something as h gets closer and closer to 0. So I want to make a definition that isn't really a definition, and it won't be a definition until we get to the next section, where we'll actually talk about limits very carefully. But right now, what happens? We have this function of h, and we'd like to know if that gets closer and closer to something as h gets closer and closer to 0. That, okay, we believe that for a car, if you take 1/10 of a second, that this should be a good approximation of the velocity, and if you took 100th of a second, it should be closer to the velocity, and 1,000th maybe closer to the velocity. As you let this h get closer and closer to 0, you expect to get closer and closer to some number that should be the velocity. Now, you don't have to get closer and closer as h gets closer and closer, but you at least want that you can make this arbitrarily close to this thing that is the instantaneous velocity by making h close enough to 0. So we make such a definition. I'll switch to y as a function of x, just because that's everybody's favorite general name for functions and variables, but it could easily be z as equals p of t. So actually, maybe in this definition I won't. This is a preliminary definition in quotes, because I'm going to use terms that are very sloppy, very intuitive. Preliminary definition of limit. So what do we have? We have some function here that's a function of h. And it's a quotient, so I'll think of it as q of h. So we say that the limit as h approaches 0 of Q of H. So think Q of H, think of it as being this kind of quotient. I mean, you can do this for any function Q of H. You can talk about this, but this is the one I have in mind, this quotient that involves H. What we'd like to know is, we'd like to talk about this thing getting closer and closer to some number as H gets closer and closer to 0. But that technically is not right. And if I ever say that, I don't really mean it. I mean, can we make this arbitrarily close to some number by making H close enough to 0? There's a subtle difference there that I may come back to. We say that the limit as H approaches 0 of Q of H exists and equals L. And we write all that by just saying, in notation, it's the limit as H approaches 0 of Q of H equals L. If and only if, so L here is a real number, if and only if we can make Q of H arbitrarily close to L by picking H close enough but unequal to. Arbitrarily close to L, except, I should say here, arbitrarily close except possibly equaling. I mean, it would be allowed to equal it, but you may not be able to do that by picking H just close to 0 but not 0. So we can make Q of H arbitrarily close to L except possibly equaling L. All right, you should realize this is not a rigorous mathematical definition. Arbitrarily close, close enough, these are kind of ambiguous terms, no real mathematical meaning. But hopefully by doing some examples, you'll understand what we're after so that when we define it carefully in the next section, it will make sense. So this is what we mean by limit. And then if we take the limit of an average rate of change, that's when we're supposed to get an instantaneous rate of change. That's what our discussion was about. So our preliminary definition of the instantaneous rate of change is what you get if you apply that to the average rate of change quotient. So this really will be our definition of the instantaneous rate of change and our definition of derivative, but it's going to rely on this kind of sloppy definition of limit. And so here's our definition, the main definition in the course. Definition. If the Q of H in this last, if the Q of H in the limit is the quotient that you get from the average rate of change. And you take the limit as h approaches 0 and the limit exists, we call that limit the instantaneous rate of change. So now let me switch to y's and x's. If the limit as h approaches 0, so you start with, you're given y equals some function of x. If the limit as h approaches 0 of f of some value of x plus h minus f of a over h exists and equals some L, then we call L the instantaneous rate of change the IROC as opposed to the AROC. IROC is kind of a famous term outside of mathematics. Some of you probably know there are cars that are called IROC cars. Yeah, it also stands for International Race of Champions. That will not be what it means during this course. If the limit of equals L, then we call L the instantaneous rate of change of f with respect to x at x equals a, the instantaneous rate of change of f with respect to x at x equals a. This IROC is also called the derivative of f at a, and is denoted f prime of a. Yeah, you read this well, the way I just said it. You read f prime of a. So this is our definition of the instantaneous rate of change, and it's motivated, for instance, by our discussion on velocity, that if f was actually p, or it doesn't have to be called p, if f is the position of an object and x, strangely, is how we're denoting time, then this is the average rate of change of position with respect to time, so it's the average velocity, but you take the average velocity as the difference, as the two times that you're using. One of them's a, and one of them gets closer and closer to being a. If, as you take a smaller and smaller time interval like that, I shouldn't say it that way. If you can make this average velocity arbitrarily close to L by making h close enough to 0, then this L is what we call the instantaneous velocity. And in general, the instantaneous rate of change. All right, let's actually do an example where we can work some stuff out, where it will become more clear of what I mean by if you take h close enough to 0, you can make this quotient arbitrarily close to L. So I want to look at an example that we looked at last time, the area of a widescreen television as a function of the diagonal length. But I'd like to simplify the numbers just so we don't deal with such ugly decimals. That means that everything we do will be kind of a gross approximation. We can just pretend that the manufacturers were a little sloppy with their dimensions, or that some of the plastic covers up some parts of the area. But I'm going to return to the widescreen television example. So let's look at an example. Of widescreen television, where we found that for 16 by 9 television, the relationship between the area and the diagonal measurement, the diagonal length, was the area is 144 over 337 times d squared. 144 over 337 is just an ugly fraction to deal with, and it gives you an ugly decimal. And we're just going to approximate this. So we're going to assume, this isn't too bad an approximation, and it certainly will make all our numbers nicer. We're going to assume that this is 2/5. This will not change any of the math that we want to look at. I mean, it'll change the numbers. It won't change any of the points that I want to make, but it sure will make the decimals look a lot better. So we'll see, this is approximately a 16 by 9 television. And I'd like to look at the instantaneous rate of change. So pretending this is what how our television's area in square inches. Yeah, this will be in square inches, while d is in inches. I'd like to look at the instantaneous rate of change of this function at d equals, pick a number, 20. So what is the IROC, the instantaneous rate of change of A, so with respect to d, when d equals 20 inches. All right. Well, here's A as a function of d, so we don't usually write we frequently don't write the of d, but I can do that now. Here's A as a function of d. And according to this, what we ought to do, according to this definition, what we want to look at is the limit as h approaches 0 we would take A of the d we want to look at is 20 inches. So you put a d plus your d value plus h minus a at your d value and divide by h. And you take the limit of this as h approaches 0. Our notation for this, if you want to get used to the derivative notation, a prime of 20 equals this. What does this mean? We'd like to see if we can make that quotient arbitrarily close to some number by picking h close enough to 0. Well, let's look at this. What do you get? A at 20 plus h. Well, that's 0.4 times 20 plus h squared minus 0.4 times 20 squared, all divided by h. Oh, and we want to take whatever this limit process means. Shouldn't stop writing that. Okay, we're assuming h is not 0. Right? We know we can't put in h equals 0 because we'll get 0 over 0. Our question is, okay, h is not 0, but can we make this arbitrarily close to some number by picking h close enough to 0. So let's do some algebra. Factor out the 0.4, square this, and we get the limit as h approaches 0 of 0.4 times, there's the 20 plus h squared, so that's 20 squared is 400, but in fact, we don't even need to square it because it's going to cancel with this squared, plus 2 times this, so plus 40h, plus h squared, and then minus this 20 squared. Right, we factored out the 0.4, all divided by h. What do you get? The 20 squareds cancel. Here's a plus 20 squared and a minus 20 squared. Those cancel. And then you can factor out an h from here and here and cancel it with this h. And so what you're left with is the limit as h approaches 0 of 0.4 times, you factor out an h from each term, cancel it with that, you get times 40 plus h. So what are we getting for the instantaneous rate of change with respect of A with respect to D when D is 20? We're getting that instantaneous rate of change, in our notation for it, the derivative of A at 20, is we're getting that it's the limit as h approaches 0 of 0.4 times 40 plus h. Well, as h gets really close to 0, does this get really close to something? Or can we make this arbitrarily close to something by picking h close enough to 0? Well, clearly if h is close to 0, 40 plus h is close to 40. And so this is 0.4 times 40, 16 square inches per inch. This is the instantaneous rate of change of the area of the television with respect to the diagonal length when the diagonal length is 20 inches. That worked out well. Okay, so well, let's do another example. So yeah, that seems reasonable, and I hope you get the idea of limit. It means, you know, what does this get arbitrarily close to is when h is close enough to 0. So yeah, in this example, it's pretty clear. If you make h closer and closer to 0, this gets closer and closer to 40, so this gets closer and closer to 16. In fact, it's just like you plugged in h equals 0, but I remind you, while you can plug in h equals 0 kind of at the end, we couldn't plug in h equals 0 at the beginning because we'd get 0 over 0. All right, well, let's calculate the instantaneous rate of change of A for D equals something else, like 40 inches. What is the instantaneous rate of change of A with respect to D when D is 40 inches? Well, what would change? We would put, so it's not this anymore, so I should, this is when D is 20. What is it when D is 40? What changes over here? We would calculate the derivative at 40, which means you put 40 here, 40 here, 40 here, 40 here. Now the 40s cancel. The cross term now, 2 times this, you get an 80h. You still get h squared, nothing else changes. Again, you factor out an h from there and there and cancel it with an h there. You get the limit as h approaches 0 of 0.4 times 80 plus h. So that if we want a prime at 40, what we're getting is it's this. It's this as h approaches 0. This approaches 80. This approaches 32. (32 square inches per inch). In fact, as you can see, the algebra that we did for calculating what happens when d is 40 and the algebra that we did to see what happens when d is 20 was exactly the same, except we replaced the 20s by 40s. It's an important fact that we can, in fact, just do this at any d coordinate just by calling it d, letting it sit there as a d, as a variable, and just know that we can pick d to be different things. This is usually, or almost always, what you want to do, because the algebra, or whatever manipulations that you have to do, will be the same no matter what d is. So we would have a d here, a d here. What would change here? We would have a d squared. So let me redo this. You would still pull out the 0.4, but now you'd square this, so you'd get a d squared plus 2dh plus h squared, and then minus a d squared. This d squared always cancels with this minus d squared. You'd factor out an h and cancel it with that. So what you're getting is that this is, so let me actually factor out the h. What you're getting, so this h cancels with that one, you're getting 0.4 times 2d plus h. Right? And so what we're getting at any d value, so just leave off the when d equals anything. What is the instantaneous rate of change of a with respect to d for any d value? You get a new function of d. It would be, here you would get 2d. As h approaches 0, this part just approaches 2d. And so what you're always getting here is 0.8 d. This is the derivative function. It's actually a function of the same variable that a was a function of. And the derivative function is what we're going to look at for the rest of the course. If you care about plugging in different d values in different problems, or different values of the independent variable, but it's important that you get an entire derivative function, not just as you calculate derivatives at just specific instances, or just specific d values. All right. Graphically, can you see this derivative? The answer is yes. You can see the derivative graphically. So what the graph of a equals 0.4 d squared. Again, I'm not going to worry about my scale too much. This is a parabola passing through the origin. It curves upward because the constant from the d squared is positive. So I'm just going to draw it kind of like I would draw pretty much any parabola. All right. So suppose we're looking at the instantaneous rate of change at 20, when d is 20. So we're back to, we found that a prime of a prime of 20, well, even if you don't remember, you can plug it in here where d is 20, you get 16. The units, which I left off here, which is not a good thing, square inches per inch, square inches per inch. What does that mean graphically? Well, we calculated this. We calculated this derivative, this instantaneous rate of change, by taking the limit of these average rates of change. But the average rates of change are slopes of secant lines. We talked about secant lines last time. So that you look at secant lines between d and d plus h, and you let the h value approach 0. What does that mean? What does that mean you're doing graphically? So here I am at d equals 20, and the corresponding point on the graph is here. So this is supposed to be a at 20, which would be a at 20. You square 20, you get 400, so you get 160. 400 times that, yes, 160. So that's supposed to represent 160. All right. The secant lines, you would move, to find a secant line, you would take some other d value, take the corresponding point on the graph, and connect those with a line. Remember, this is a secant line to the graph. It's a secant line for this function. That color is not going to show up very well. Let's try green. You connect those lines, those points to get a line. Great. So here we are at 20 plus something, but call it 20 plus h, and think about what happens as h gets close to 0. So when h is smaller than the h I've got pictured here, you would be in here. This point would be fixed. I should have been more careful. This secant line, what's the point of drawing the secant line? Its slope is the average rate of change. The slope of this secant line is the average rate of change of the function between d equals 20 and d equals 20 plus h. Right? So its slope is this. The instantaneous rate of change is the limit of that. So it's a limit of some slopes. Slopes of what? Slopes of lines, but now we keep moving the second point on the graph closer and closer to this point. So corresponding to this d coordinate, you would get this line, or this point. And now I'm going to have trouble distinguishing my lines from the curve, but you take a line connecting those 2 points. And you keep doing this as the point changes, you keep moving your line to connect this point and these closer and closer points. Eventually, you arrive at this line. It just kind of glances off of the curve right there. Right? I hope you can picture this. It's kind of hard to draw with chalk on a board. But as you take secant lines and the second point moves closer to this point, your secant line kind of, at least in this picture, as your point moves closer, your second d coordinate moves closer to 20, the corresponding point on the graph slides down here. The line connecting them kind of pivots. And in the end, you should picture it as just glancing off of the curve at that point as you try to connect points that are closer and closer together on the graph. This is called a tangent line. It's intuitively, you think of it as a line that just glances off of the graph at a point. That's not quite true, as we'll see later. If the curve does something called inflecting, it doesn't really look like the tangent line glances off of the curve at the point. But that's a good first way to think of it. The tangent line, this thing is called a tangent line to the graph. And its slope is the limit of the slopes of the secant lines. So the tangent line has slope equal to the limit as h approaches 0 of the slopes of the secant lines. But the slope of the secant line, is an average rate of change. This is the limit of the average rates of change. It's the instantaneous rate of change. It's the derivative. So the tangent line has slope equal to the limit as h of the slopes of the secant lines, i.e. its slope in this example is a prime at 20. It's the derivative evaluated at the point in question. So in this example, this was the 16 as a slope. I'm going to drop the units where I think of slope as a purely mathematical thing. But so yeah, you can picture instantaneous rates of change on a graph by just taking the slope of these tangent lines, these lines that just glance off of the graph at the point in question. It also means that you can write an equation for the tangent line. So an equation for the tangent line in calculus, there's one form of an equation of a line that comes up more often than other forms. It's the point slope form of a line, because the derivative, the instantaneous rate of change, the derivative tells you the slope of the tangent line, and you know where you're calculating a point on the line because you know where you're calculating the derivative. You're calculating it, for instance, here we were calculating it when d is 20, which means the y-coordinate is 160. So you know a point on the line, this derivative, if you can calculate it, gives you the slope of the line, and then you use the point slope form of the line. Unless you're told to use some other form, this is certainly the form you would want to use. So in terms of A and D, what's an equation for the tangent line? So we're a point on the line, is 20, 160. The slope of the line is 16. So an equation for that tangent line, you think y minus the y-coordinate, but it's a, not y, here, equals the slope, 16, times, think x minus the x-coordinate, but here it's d, so d minus 20. I just leave the answer like this. If you're told that you have to write it in slope-intercept form, yeah, you can put the 160 over here and multiply this out. But this is a perfectly good equation for a line. All right. So what have we done? We've talked about how you kind of intuitively go from average rates of change to instantaneous rates of change. The instantaneous rate of change at a fixed value of the independent variable, you take a limit as the change in that variable approaches 0 of the average rates of change. But we haven't given a really, even close to a mathematical definition of limit, which is what we have to do in the next section. The next section is very technical, and what you ought to get out of this is that the idea of the derivative, the idea of the instantaneous rate of change as a limit of average rates of change. I should also say that we need some rules for calculating these instantaneous rates of change. We don't want to have to go through the algebra every time to derive what these limits are. You could take kind of arbitrarily bad functions. The one I'm about to write isn't even as bad as a lot of them. But suppose I took the position of a particle with respect to time as 1 over the square root of t cubed plus 1, at least for t greater than 0. Suppose I took this function. How bad is it to calculate just by doing the algebra the limit as h approaches 0 of p of t plus h, where t could be anything, minus p of t over h? Well, I'll let you look at the example written out in the book, but it's painful. And we can do the algebra, but it is not fun. And it's also not quick. And what we'd like to do, and what we will do in later sections of the book, not only is make the definition of a limit rigorous, so really mathematical, but we have to come up with rules for calculating these derivatives, these limits of quotients, that's faster than redoing the algebra all the time. And once you have all these rules that will tell you quickly how to come up with answers to these things, there's a tendency to forget why we define the derivative the way that we do. Or you just forget what derivative means. That by its definition, it's the instantaneous rate of change because it's the limit of average rates of change. And really, it's sad that lots of students come out of calculus courses remembering the rules and somehow not remembering that the derivative is the instantaneous rate of change. And why is it the instantaneous rate of change? Because it's defined to be the limit of the average rates of change. And while you may not calculate with the definition very often, it's the definition that gives you all of the applications, because it's the definition that makes it the derivative the instantaneous rate of change. So don't forget. Once you have all the rules, don't think that the rules are what the derivative is. The derivative is the limit of the average rates of change. The rules just help us calculate this thing that we care about so much. Next time, we'll have to do limits, and it will be technical, it will be ugly, but we have to do it at least somewhat.